Afternoon there, guys. Today I'm going to finish off talking about the gravity and satellite section. First of all, we have a little bit of a refresher about centripetal forces and centripetal acceleration. So remember, an object going in a circle, VI, VF, if we take VF plus and minus the VI, so we're just going to add the negative of vector, we end up somewhere around here. I'm doing this really quickly because hopefully you can remember it. Delta V is towards center, and it's always perpendicular to motion. I'll just say perpendicular to the motion. So it's always at right angles. Doesn't speed it up, doesn't slow it down, always changes its direction though. The other thing about it is, because we've got this change in velocity, it must mean we've got an acceleration. If we've got an acceleration, it must mean we've got a force, which means that the force is also in the same direction as the acceleration and the change in velocity, which is towards the centre of the circle, which is also perpendicular to its motion. Doesn't speed it up, doesn't slow it down, just changes direction. The important thing to remember about the force is that it's constant. So if our change in velocity over time is constant, our acceleration is, and so is the force. So we've always got this constant force. It doesn't change size. We need this for uniform circular motion. So for a centripetal force and causing something to go in orbit, let's imagine that this orbital path here is one of our satellites. We've always got this force. This force is governed by Newton's law of universal gravitation, m1, m2 on r squared. The radius doesn't change, the masses don't change, gravitational constant doesn't change, the force doesn't change, which means that this force here must be, all of these things, must be constant, must be perpendicular to motion, and it must also be towards the centre. Alright, now what this kind of means is that, let's use the Earth, there's the centre of the Earth. Every single orbital satellite, so geostationary, that's way out here, and polar orbiting ones that are going north-south, north-south, or south-north, south-north, always have to rotate about that exact point there. What it means is that this force that's directed towards the centre, force must be towards the centre of the circle for UCM, uniform circular motion, which means it can actually orbit. Without this, without the force being towards the centre of the circle, without it being constant, without it being perpendicular to the motion of the satellite, it will not undergo this. It is not undergoing uniform circular motion, it's gone non-uniform, which isn't a satellite anymore, that's just something whizzing around the Earth, likely to crash into Earth. Okay, so for all of these satellites, I'll stick with the ones that are going around the equator. They're the geostationary ones. So huge, big orbits like this. The centre of this path is always towards the centre of the Earth, as if it's just a singular point, as if you are spinning this satellite around as if it's a rock and a piece of string, and the piece of string is, the centre of it is your hand, and your hand's the centre of the Earth, and all those sorts of cool things. There's only one orbital path for it. It can't orbit down here because the force is coming from this direction. Now we haven't got a force that's constant. We haven't got a force that's always towards the centre of the circle, because when it's down here, the force is up in that direction. When it's here, it's up in that direction. They're not pointing they're not always pointing at the same kind of point in the same sort of way. It's kind of weird, but it's actually trying to bring this orbit upwards, because the force isn't just towards the centre of the circle, it's towards the centre of the circle and pulling it upwards. So now you haven't got a uniform path, and we need a uniform path. Now, geostationary satellites, hopefully you've done the calculation by now and you've worked out that they orbit somewhere around 36,000 kilometres above Earth. Alright, so you've got this satellite that's 36,000 k's up. It's no good for surveillance. We don't have cameras that are that great. We've got telescopes that are that great, but definitely not cameras. So these things can be used for GPS. They can be used for communication. They can be used for weather, alright, but this satellite that's orbiting here, it can see stuff underneath it really well. So remember, it sits above the same point on the equator all of the time, so it can see things that are underneath it. So it can see, you know, things that are on the equator, but it can't really see, you know, it's too far down. In Australia, we're kind of lucky that our geostationary ones, so the Foxtel dish or the satellite, the hostile dish that I've got at home, it points, you know, kind of out that way, north and a little bit east, towards this geostationary satellite. Points there all the time. That satellite can obviously see my house. It can probably therefore see the weather above my house, but it can't really see too much further south. So if you're in Tasmania, this wouldn't be much good. If you were the northern parts of North America, this wouldn't be much good, because you just can't see it well enough. Alright, so sometimes for GPS, for communication and weather, if you're near the equator. The other type are polar orbiting satellites, and they're the ones that go around the poles. So these don't have, you know, fixed, you know, one set sort of radius of orbit. They've kind of got a range, and they're usually somewhere, I'm going to say around 400 k's up to about 2500. Okay, so they're much closer. So again, these can be used for GPS. So we can triangulate between, you know, a range of different satellites to find out how far we are away from all of them, which means we'll be able to find our position. Because they're a hell of a lot closer, 400 k's, 2500 k's, we can also use them for mapping, and we can use them for weather, and we can use them for surveillance. Alright, because they've got cameras on there that are able to see, you know, a fair way, you know, this sort of range, you can actually do that sort of thing. So Google Maps or Google Earth use these types of satellites. There's hundreds of them up there. Australia has access to a network of them, and they're actually really handy. Now the last part that I want to talk to you about is the way that we launch all of these satellites. So with the ones that go around the Earth, they'll kind of do, I guess. But when we're launching the ones that go around the equator, so we have, you know, geostationary ones are around the equator, but we also have a range of, you know, smaller orbits that are around the equator too. We know that the Earth is rotating not east to west, it's actually rotating west to east, so the western part of Australia is behind. It's always trying to catch up. You know, so Perth is behind us in time zones, we're behind the eastern states in time zones. So the Earth is actually rotating that way. So what NASA has decided to do, and it's actually pretty damn clever, they launch their satellites in that direction as well. Because what you're using is the about 1600 k's an hour that the equator is actually doing through space. Remember, you're trying to get this satellite into orbit around Earth. It's not inside our atmosphere anymore, it's outside, so there's nothing, like there's no atmosphere to kind of hold it in place and keep it moving around like a swimming in a liquid. So we can launch them west to east. We can pick up this bonus 1600 k's an hour in our launch speed. What that allows us to do is either burn less fuel, or usually, hopefully you can read that, more payload. So it'll be cheaper to launch the thing with the same amount of gear on board, or what they'll usually do is leave the same amount of fuel on it but just load the satellite up a little bit more. So they'll put more technology on it. So it might now be able to do this, or it might have a better camera on it, or it might have better surveillance equipment, so it can you know, GPS signals and all that sort of stuff, but also triangulate data a hell of a lot better, and encode it, encrypt it, all that sort of carry on. Okay, so satellites really kind of cool. They're actually kind of strange when you think about it. There's all these things flying through space, but they're also flying around Earth, so they're doing, you know, all of these weird sort of patterns, except for that one down the bottom, because remember, that can't exist. The Earth wears a belt. The belt goes around its waist, not around its knees or around its throat. Alright, and that there is also the application for this section.